Right. So in the previous two videos, we looked at agents, we looked at the environments they operate under. Now let's try and define what a problem in an AI space would look like. But what you realize is that we have got real world problems that we have, and we are trying to use machines to solve those problems for us. Not necessarily because that humans can't. There are some scenarios that humans can, and there's some where they can't. So if you look at chess, we know humans can play chess, but we have now machines that can play chess better than human beings. So that is problems that we have. But a problem definition to a human being is different from a problem definition to an agent, an AI agent. So we need to define what a problem to an agent should look like, should consist, and should have. All right. So let's look at some definitions here. For any problem, right, we can have what we call a goal formulation. So we want to see, based on what we currently have and how happy our agent is or the performance of the agent is, we need to find whether or not it is our desired goal. The first thing we need to do when we have a problem is to formulate a goal. What is the end point? So you want to define the starting point and the end point to avoid an open-ended problem. If you want to formulate a problem, right, you are deciding on the actions instead to consider given a goal. You are saying you are choosing the tools or the potential tools that will be used in this problem given a specific goal. Right. So remember my example about trying to measure or trying to see what happens at the core of the earth. And then we found out that using a metallic arm is not the best way to do it. Why? Because metal melts. But if you are going to use spectral analysis or image processing, then we see that, well, that could work. Right? We're choosing the actions to consider. Then we have a search algorithm, right? It is something that takes a problem as input and returns a solution in the form of an action sequence. Right? So what does this mean? If you have a search algorithm, you simply give it the problem. Right? And then what does it give back? It says, this is the problem. Then if you want to get to the solution, do 1, 2, 3, 4, and so that's a search algorithm. It goes through the process of figuring out what will happen if you take the different path. So think of this as a maze. Right? And you are the search algorithm. You've got a maze and it has got multiple paths. So before you actually go through, you want to first find the correct path that leads to the goal. And then you can take it. Right? So why is this helpful? This is helpful because it avoids you doing the actual work of going through all the different paths. Remember, we talked about dynamism and static environment. In a nutshell, while the agent is executing a solution, it ignores percepts. Right? The moment we choose on a solution to take, we then choose to ignore the percepts. What does it mean? We choose to ignore inputs, further inputs, up until I finish in execution. If you have something that is slow to execute, if you have something that is slow to execute, then you have a problem. That's why computational power has been a blessing in the recent age of artificial intelligence, because they can respond fast enough and execute a solution fast enough so that if the environment changes, you can also change. In cars nowadays, this a video came up on YouTube ads about the new Ford Ranger. So the new Ford Ranger it has got adaptive cruise control. So ordinarily, cruise control previously, what it did was it would say, look, I'm going to be traveling at 120, so I push the button for cruise control. The moment I hit the brakes, right, cruise control goes off. Nowadays, we have adaptive cruise control. So I want to travel at 120 kilometers per hour. But if the car senses an obstruction in front of it, a moving obstruction, it is going to slow down up until the road ahead of it is empty. So you don't necessarily have to press brakes anymore, right? All you need to do is to go to the other lane, overtake, and it speeds up again to 120. So that is adaptive speed control or cruise control. Now think of this. It took long. If it took long for the car to react, it then says, okay, you need to slow down. For it to get to the decision of it slowing down, it took 5 seconds to do that. What is the impact? What can happen in 5 seconds? But if it can happen in microseconds, then it means your reaction time is far much more better, and you can avoid collisions. You have got a lot of time to chip in and react if any one of the safety checks fail. So this computational power is leading to advancements like, say, for example, the adaptive cruise control that I've just. What is the problem? In AI, or for an agent, right, a problem needs to have 5 components, right? So we need to identify the starting state, a problem. Where do we start? So after we know where we start, then we need to be able to describe the possible actions available for the agent. What can the agent do given that they're starting in this start state? So if you're given a particular state S, the action S, right, it should return a section of actions that can be executed by S. So it brings back all the possible actions that can be given by S. Then number 3, we need a description of what each action does. Right? So we need to know if we're in state 1 and we take action X, what is the result? Right. Then we can say, well, it is a deterministic environment, or it's stochastic, right? So that is the description of the action. And then we need a goal test. After each action, if we reach a goal, is this a goal? So that is the question to then ask. Right. Then number 5, we need to evaluate our action and see how good it was. So each action that we take, we have what we call a path cost function, which assigns a numeric cost to a path. Right. So the agent chooses a cost function that reflects its own performance measure. So remember, we talked about rational agents and so forth. So a path cost function is a value, and it is an actual value. All right. So let's look at this map of Romania. If someone wants to start at Arad and end, say, in Bucharest, right? If you notice, I have already given a start state and I've defined the goal formulation, right? So if I want to move from there to that, what am I going to do? I'm then going to say, right, I've defined the start state. What are the actions that are available? Right? For this state, what are the actions that are available? I can take path A or path B, right? Or path C, right? And then what is the result of that action? if I am in Arad and I take action C, so action the state Arad and take C, then I'm going to end in Zerin, if that is the correct pronunciation. If I take A, I'm going to end in Sibiu. If I take B, I'm going to end in Timis. Right, in there. So I have an output for each action that I take. Then goal test. Is Zerin a goal? No. Is Sibiu a goal? No. Is Timisoara a goal? No. Right. So that is the goal test. So if we then reach Bucharest, then we know that we can then say, is it goal? Then we're going to have yes. All right. So we have got the goal test, and now we have got the path cost function. So we then see, okay, if we take A, the path cost is 140. If we take B, the path cost is 75. If we take C, B is 118 and C is 75. So based on the performance measure of the agent, we can choose, or the search algorithm, based on the search algorithm, we can choose which path to take first. So that's a problem definition. However, a problem can be defined by a state space. Right? A state space looks at the initial state. If you can have an initial state, the actions to be taken, and the transition model, then you have got a. So if you have these three, they give you a state space. So lastly, let's look at the concept of abstraction. Right. Not all information is important to the resolution of a problem. Not all information is important to the resolution of a problem. So we need to be able to abstract or to remove information that will not assist in the solution of the problem. So that's that. Let's call it, and we'll meet in the next video when we look at examples of problems.